everyone, I'm Yuedan Chen from Hunan University in China. Today, I will talk about our work exploiting hierarchical parallelism and reusability in tensor kernel processing on heterogeneous HPC systems. This is a joint work with Data System Group in University of Waterloo and the University of Sydney. Many data-driven applications involve sparse tensor data. The tensor data can be regarded as a multi-dimensional array used to represent the multi-way data, and the sparse tensors usually contain a very small number of non-zero elements. In addition, sparse tensor decomposition is an effective and important tool for many data-driven applications. For example, tensor decomposition used in recommender systems provides a fast, interpretable, and competitive method to produce the embedding and relations hidden in sparse tensors. However, the bottleneck cost of tensor decomposition is an operator called MTTKRP. The MTTKRP on a dimension multiplies the matrix of the tensor unfolded along the corresponding dimension with a result matrix of Cottrell product on two-factor matrices. Therefore, any application that uses tensor decomposition will benefit from acceleration of MTTKRP. To accelerate sparse tensor kernels, many studies make use of HPC architectures. Heterogeneous HPC architectures with advanced performance are prevalent nowadays due to the combination of complicated control CPUs and many-core or multi-core accelerators. Therefore, accelerating sparse MTTKRP on heterogeneous HPC system is effective. However, there are four main challenges to do this. The first challenge is how to use tiling to map MTTKRP to the underlying systems. For example, the n-dimensional tensor tiling method divides the tensor into smaller n-dimensional blocks to parallelize the MTTKRP, but it generates extra internode communication. To overcome this, the rank tiling method partitions the given factor matrices along the row dimensions, but it needed to replicate the tensor data without considering the data reusability. In addition, this tiling method do not consider the limited device memory of each GPU. Therefore, designing an efficient tiling engine requires pay attention to the balance between data reusability, multi-level parallelism, limited device memory, and intranode or internode communication. The second challenge is how to optimize MTTKRP on each GPU. The sparsity of tensor data leads to random memory accesses and underutilization of memory bandwidth within each GPU. The third challenge is how to design the appropriate data structure. For example, the standard column-wise CSC sparse tensor storage has the problem of redundant and random indexing in sparse MTTKRP. And the last challenge is how to optimize the tile size. Manually tuning the tile size usually involves trial, which requires considerable manual effort and resulting loss of accuracy. To address the aforementioned challenges, we propose a new approach called HPSPTM that can exploit the hierarchical parallelism and reusability in sparse MTTKRP on heterogeneous CPU and GPU HPC systems. HPSPTM incorporates four techniques. The first technique is the tiny engine that can efficiently map a sparse MTTKRP to the underlying systems. We have three considerations to design the tiny engine. The first consideration is tiny along I dimension and R dimension can avoid internode communication, while the I dimension is defined as the row dimension of the unfolded tensor, and the R dimension is the column dimension of the two-factor matrices B and C. The second consideration is each row of B and C reuses a subset of columns in the unfolded tensor. And the third consideration is fine-grained tiling of the unfolded tensor could generate more empty columns. To address these problems, we first propose the factor matrix-driven MTTKRP algorithm to utilize the data reused by each row of the two-factor matrices. Based on it, our tiny method has three steps. The first two steps tiles the MTTKRP along I dimension and R dimension to exploit the process-level parallelism between computing nodes and the thread-level parallelism between GPU threads in each node. Especially according to the factor matrix-driven MTTKRP algorithm, we can find that the row 1 of the process-level block of B is reused by two empty columns in the process-level block of the tensor. These columns and rows do not contribute to the result, so before the thread-level tiling, we first eliminate them to reduce the memory usage. And next, to leverage the limited device memory of each GPU, the third step of the tiny engine partitions the thread-level blocks along I and R dimensions, and then further partition along the row dimensions of B and C to get several fine-grained tiles. Therefore, as shown in this figure, according to the factor matrix-driven MTTKRP algorithm, the two tensor tiles colored in yellow will be multiplied with a tile of B colored in red and the only one tile of C colored in purple. The second technique in this work is the tensor-driven parallel execution that can optimize the efficiency of MTTKRP on each GPU. We consider two observations. The first observation is the no empty columns of the unfolded tensor have random positions. So in the factor matrix-driven MTTKRP algorithm, another search is needed to find the no empty columns that will be multiplied with a given B row and a C row. Another observation is a B tile and a C tile will reuse a subset of tensor tiles. To exploit this, we first derive the tensor-driven MTTKRP algorithm, so columns of the unfolded tensor can directly index and access the required row of B and C. Based on this algorithm, we adopt a tensor-driven buffering technique that can allow each tile of B and C to stay in the device memory of each GPU, and then the required tensor tiles are successively fetched from host memory to device memory for computation, so that the bandwidth demand is reduced. To further optimize the performance, we use the pipeline technique. As shown in the figure, while performing parallel computation on the current set of tensor tiles, the next set of tensor tiles required by the same buffered B and C tiles can be streamed in the same time. Therefore, fetching tiles from host memory to device memory can be performed in parallel with the computation on the GPU. Moreover, due to the different sparsity levels, different tensor tiles could have different data transfer cost and computing cost. So we exploit this by processing the tensor tiles in descending order of the number of non-zeros they contain. As shown in the figure, better overlap between the communication and computation could be achieved. The third solution in this work is the data storage. We first study the standard CSC sparse tensor format. It is a popular column-wise storage by using 3 arrays. The first array stores the pointers to the start and end positions of each column. The second array stores the row index of each non-zero. And the third array stores the value of each non-zero. However, there are two main defects of the CSC storage. The first defect is we can find that there are many redundant index data for empty columns in the first array. But if the CSC only stores the no-empty columns, their column indices in the original tensor cannot be retained. To address the problems, we develop a partition-aware lightweight data storage that improves upon CSC to preserve the column-wise simplicity of CSC and support efficient data access patterns and reduce memory usage. The first step of the data storage is tile permutation. According to our diagram execution design, we first group the tensor tiles that are required by each B tile and C tile. Then, according to the aforementioned pipeline technique, the tensor tiles are permuted to better overlap the communication and computation. So we permute the tiles in each group in same way to support the execution design. This step ensures that all non-empty columns can be accessed contiguously. The next step is storing the permuted tiles in 4 arrays. The first array stores the pointers to the start and end positions of each non-empty columns. And the second array stores the original index of each non-empty column. The last 2 arrays respectively store the row index and the numerical value of each non-zero. Therefore, in our data storage, only non-empty columns are stored, and their original indices are stored as well. The fourth solution in our work is auto-tuning the tile size based on the performance analysis. And the adjustable tile size is 4 parameters, that is lambda, phi, omega, and gamma. We first analyze the value range of the 4 parameters. Considering the limitation of device memory size on each GPU, we analyze the upper bounds of the 4 parameters. In addition, according to the performance of data swapping within each GPU, we further add constraints on the tile size to optimize the bandwidth. We further establish the runtime model of HPSPTM by analyzing the parallel computer time and data swapping time. Based on this, we transform the tile size auto-tuning into solving an optimization problem, where the runtime model is the object function and the parameter analysis provides the constraints. Next, I will introduce the performance results of HPSPTM. We select 6 real-world datasets extracted from applications in different fields. HPSPTM is tested in 3 environments. The first environment is the single CPU and GPU machine. The second is the multi-GPU machine that is equipped with 8 GPU cards. And the third environment is the Sunway Tachylite supercomputer that contains a very large number of heterogeneous and many-core Sunway processors. And the architecture of Sunway processor is quite different from the CPU and GPU machine. In addition, we test our work by comparing with 3 state-of-the-art techniques. We first show the thread-level scalability on a single GPU. HPSPTM performs better scalability than competitors. And this figure shows the runtime of HPSPTM and the 3 competitors. Our work outperforms the competitors. This is because the auto-tuned tiny method enables more compact storage of sparse tensors and larger data reusability. In addition, our tensor-driven execution supports the efficient data access patterns. We further test HPSPTM on 2 different high-performance computing architectures. The result reveals that HPSPTM also performs well on other heterogeneous architectures with several minor adjustments by considering the hardware characteristics. In conclusion, HPSPTM incorporates the auto-tune tiny engine and the tensor-driven parallel execution and the design-specific lightweight data storage to exploit the hierarchical parallelism and reusability for sparse MTTKRP on heterogeneous HPC systems. Thank you for your time.